Hello, welcome back to CSC 263 Database Management Systems at Adelphi University. In the previous few videos, we looked at how we can use the database management system to secure the data in our database. Specifically, we talked about cryptography in the previous video, and in the video before that, we talked about authentication and access control. This week's topic is a little different. Because what we're going to do is not look at how the database management system protects data, but how your database application plays a role in the protection as well. So we're going to be looking a little bit at network security. We're going to look a little bit at application security. Now, it's fair to say that both network security and application security would be topics for a full semester self-contained course. So what we're doing here is briefly touch on those topics to frame how they fit within the overall picture of database security. But of course, I cannot do a full deep dive in application and network security here. So when we think back to our database architecture, we see that the database management system interacts with the database application, and that often happens via a network connection. And that means that we have an ability to do some security there. Not a whole lot, because a network is just a network. But one of the ways we can do this is through the correct use of firewalls and intrusion detection or intrusion prevention systems. Now, I do have to say that as we start seeing an increasingly mobile workforce, as we start seeing applications that are becoming more and more web-based, the concept of using network protections, specifically perimeter-based network protections, is becoming less and less valuable. Yet there is still some protection to be gained from it, so let's briefly discuss those. If I have my database server sitting on my network, somewhere connected to the internet, I hope that at least at this point in the game, that the database connection is not open to the internet without any restrictions. Ideally, the database connection is not open to the internet, period. But that's a whole different story. We want to run our database management system on a somewhat trusted network. We definitely do not trust the internet. And we have these devices called firewalls, and the whole point of the firewall is to separate the trusted part of the internet from the untrusted part of the internet. And by doing so, it provides a single point of control and a single point of audit for network traffic. And so, if we deploy our database management systems to a network, then we have to think about how do our database applications connect to the server. Do they use, for example, a TCP port? And if so, what is the port number? What is the protocol they will be using? Etc., etc. At that point, we have some abilities to screen some of the network traffic that might originate from the internet or from another untrusted location and prevent it from reaching the network that has the database management system in the first place. So that's called the firewall. The firewall should be configured to only allow traffic to and from the firewall that matches the firewall's specifications. And notice that I said to and from. You really want to figure out to filter traffic bidirectionally, not just from the internet to the server, but also from the server to the internet. Now there's still some channel then that allows internet-based traffic to go to the database. Otherwise, what's the point of connecting it to the internet? The firewall itself usually can't see how trustworthy that traffic is. For that, we need a secondary system, which is called an intrusion prevention or an intrusion detection system. The IDS is a system that looks at the traffic but does not block it. It just shows alerts. But the IPS, the intrusion prevention system, will actually block traffic that it deems to be suspicious. And as such, it adds an extra layer of protection onto the firewall. It also adds a check to make sure that the firewall is working correctly. Now, ideally, all network traffic between the database and its endpoints is encrypted using TLS, the Transport Layer Security Protocol Suite. And that makes especially the IDS IPS option less effective, because all it will see is encrypted traffic. The alternative would be to provide the IDS IPS with the encryption keys or the certificates that are used by the database management server, so it can still inspect, but that's also not ideal. All in all, there is some stuff we can do in terms of network security, but it's not a whole lot. The vast majority of the protection of your database application will have to come from the database application itself and the operating system on which it is deployed. Now, when we talk about application security, we talk about security, or insecurity maybe is a better word, caused by the way in which programs are written. Now, we all have programmed before. We all have tried to compile our program and then found out that there were errors in it. That's not a security problem. That's just a syntax error. Right? But we've also had situations in which our program started crashing at random times and started behaving unexpectedly, and that could potentially be a security problem, especially when it deals with errors that happen only under certain circumstances. You know, it's time to start taking an extra hard look. Not just assume that whatever your program is going to do, what input it's going to be given, is going to be perfectly crafted input. And that brings us to the first rule of application security, and maybe by far the most important rule: never trust input. It does not matter where the input is coming from. You may never trust the input before you have checked the input to be trustworthy. Then, if you want to be a nice neighbor to other applications, also make sure that before your program generates any output, that output is clean also. If just those two rules stick in your head, never trust any input and always sanitize your output, the internet has just become a whole lot safer. That sounds easy, but look at the diagram and see where a typical application takes input. You know, the most obvious one is my database application in the middle. Will probably take some form of user input. How that user provides the input is kind of irrelevant, whether it's by clicking on a button in a graphical user interface, or typing stuff on the command line, or submitting stuff via a web form. It really doesn't matter. It's user provided input, which arguably is one of the most dangerous ones, because you don't control your users. So anything you receive from your users always must be checked to see if it is in line with what you expected it to be. If it is not, reject the input. Simple as that. But there are other input sources as well. For example, your database application probably at some point interacts with the file system. Maybe that's where it gets configuration options from. Maybe that's where it keeps temporary state. And even though the assumption is that whatever you write to the file system is how you find it back, you might be on a multi-user system. You most likely are, where a system administrator has access, and maybe an attacker has access as well, who might be changing your configuration files or your other files that you read as input. So always verify what you read from disk. Obviously, you can take input via the network. Well, the network and your user input are pretty much on the same level of trustworthiness. None. So clearly check that as well. But there's a lot more to it. For example, if you're dealing with web applications, now we have cookies that we can be using as input. Little bits of data that are set in the HTTP headers. But the headers are sent by the browser, and the browser is under the control of the user. So that's something to keep in mind on. Every application also runs on an operating system, and the operating system also has a way to interact with your application. It could send signals, for example, that say stop running and start closing down gracefully, or a signal that might say, hey, please reload your configuration file because it's time for something, or maybe, pause execution, or, whatever it may be. There's signals that the OS can send. And if your application receives that, do you know how it's going to respond to that? It might be through environment variables. An environment variable is a very useful mechanism to influence the runtime behavior of your system at launch time. It's a good way to set, for example, configuration options, but are you sanitizing them? Command line arguments, same thing, are you sanitizing them? All of those are inputs. Specifically for this course, anything that you store in the database management system and then at a later point retrieve from the DBMS again is also input to your application. And the DBMS is most likely a shared database management system that has other users on it and has other people interacting with the data. And that means that you should not trust the data coming back from the DBMS without verifying that it is indeed trustworthy data. So there's a lot of complexity to writing proper applications, and this is just the tip of the iceberg. I want to dig in on one specific example that is highly relevant to developing database applications. But before we do that, let's take a quick peek at what a database application generally looks like. Let's say that we have a web-based database application. On the left we have our users. In this case, one of them might be a malicious user who is operating a web browser. Now keep in mind that the web browser is 100% under the control of that user, of that attacker, and that means that whatever originates from that web browser cannot be trusted. So I might have my URL, example.com, and I might have some form data that I'm posting to my web application that is running on the web server. The web application will also consult a DBMS in the back end to run some queries, which then return some output to the end user. In this particular case, there is a field in my web application that is vulnerable to a specific type of problem called SQL injection. And so, what is that? Let's take a look at this first code example here. Cursor.execute, open parentheses, open quotes, select credit limit from customers where customer ID is, double quotes to end the hard-coded string, plus the customer ID, which may have been whatever field the user provided. At this point, you have vulnerable code. It will work when people follow the rules. When you put in customer ID 1, this query will execute and retrieve the credit limit of customer ID 1. But this is not the right way to do it. And the main reason for it is that this query is meant to retrieve the credit limit of one particular customer that is named by ID. That's the intent of the programmer when he wrote this, or she wrote this. Now, let's take a look and see what happens if we take that same magic value that we just saw up here, that quote or 1 = 1 semicolon dash dash, and stick that in here. Oh, in this case it's 0 or 1 = 1 dash dash. So why is that a problem? Well, look at what the query becomes. The query now becomes, with that input, so 0 or 1 = 1 semicolon dash dash, it becomes select credit limit from customers where customer ID = 0. That's exactly what we expected. But the query then continues, or 1 = 1 semicolon. Oh, I flipped them around there. I'll fix that. So we're going to return the credit limit of the first user, of user ID 0, customer ID 0, sorry, or all of the credit limits for customers where the value 1 equals the value 1, which is always. And what I've done now is change the behavior of my query. The semicolon in my input forces it to execute. The double dash is SQL syntax for a comment, so anything after the double dash will be ignored. And I can do all kinds of bad things to this. Instead, for example, I could update data. I could delete data from the database. I can drop entire tables if those permissions haven't been tightened down enough. So this is bad. Just taking the user input and gluing it onto the end of a string and then passing that string over to the database basically says, hey, end user, you can execute strings directly onto the database, which you've just built out all of those network protections to prevent that from happening. And here you give that conduit again. So this is not the right way of doing it. So the way to solve this is by telling your programming language and your database management system which parts of the query are trustworthy and which parts are not trustworthy and should be removed from all special meanings. And so by doing that, which is sometimes called a parameterized query, we can let the systems make informed decisions about what to do and what not to do. In our lab environment, we use the psychopg2 library as a Python library as a library to connect to the Postgres database. And in Postgres, it's really simple. Anytime that you want to put input into your application, put a little %s in your query, and then at the end of your query, just list out what those %s's should be. The %s is a placeholder, and then outside as a second argument to your execute is a tuple of the values which are provided in the order in which you specified the %s's in the string. Notice that you'll also always use %s. It doesn't matter whether you're putting a number, a date, whatever data field you want. It's always %s as a placeholder. And now your programming language or the library, psychopg2 and the DBMS can separate out between what is trustworthy content and what isn't. And in the non-trustworthy content, the special meanings like semicolons and double dashes go away, then all of a sudden the query will fail. And so that is preventing SQL injection. It's a very simple code change, but it has major impacts. And so there are many of these examples, things that you can do in multiple ways where one is better than the other. As we continue going through our program here at the computer science program, especially if you're in the cybersecurity specialization, you'll see more and more of these examples as we go along. Okay, so that's it for database security. We've talked about the need for security, confidentiality, integrity, availability. We talked about how the database management system can help, first through its entity integrity, domain integrity, referential integrity, and its check constraints. Secondly, by developing an authentication and access control system and audit trails, and also that the database applications that we are writing against our DBMS have to be deployed in a secure network connected way and written in a proper format. Once we have all of that in place, we have a reasonable assurance of security. But as always in the field of cybersecurity, you have to be 100% correct all of the time. And that makes it such a hard field to work in.